These are all brand new questions. I made them all up. I've never given this quiz before, so let's see. In a flat corner with a 30-meter radius, a car barely negotiates a turn. If mu equals blah, 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 how fast is it going? This is a question that I like. This is a question that I like. So this would be fair game as a written question going around a flat corner. I would either give you the speed and say find mu, or I would give you mu and say find the speed. The key here was to recognize that this was a good job for a free body diagram, and I recommended that you draw a front view. I usually had the center of the circle on the right, and I showed that by drawing a little loopy arrow, and then I said, okay, the car has tires like that. There's the body of the car, the headlights pointing towards me. That was usually enough that I could figure out my directions. Again, Matt, you don't have to draw the car. You can represent it with a dot. I'm still enough of a child that I enjoy drawing a stick-figure car. What are the forces acting on it? Get the obvious one. I have gravity down. I have normal force up. What path is this car tracing out? It's tracing out a circle. So I know there has to be a force toward the center. What force is that? Friction. Those three red lines, if I said draw the free body diagram, that's the free body diagram. What doesn't appear on the free body diagram ever? FC. Does not. That's going to be a big temptation for some of you. There will be a question on your test where I do ask you to draw a free body diagram, something. Don't put FC on your free body diagram, please. As an equation, it looks like what I get is friction is what's pushing me in a circle. Mu times the normal force equals mv squared over r. I guess I could also ask the period, but when you're going around a corner, are you completing a full circle when you? So it wouldn't make much sense. Maybe if I was doing a circular racetrack and asking how long it would take to do one lap, I guess, but that's to me a wishy-washy meh of a question. I don't know the normal force. Oh yes, I do. It's the same size as the normal force. The mass cancels. Yay! What do they want me to find? How fast? So here, as far as I'm concerned, asking you to solve for mu or v or r, totally fair game for either any three of those. In fact, I made up 4 versions of the test. The odds are pretty good. If I did use this question, on one of the versions you're finding mu, on another version you're finding r, on another version you're finding v, and in the 4th version you're finding one of those 3. I don't know. Here I want the speed. I get v equals the square root of mu ger. I smile because that lets me know whenever I see that, I'm probably doing it right. It's going to be 0.655 times 9.8 times 30. I hope these are good answers because I was just making up numbers. Do you get 13.9? So if you got that, 3 out of 3. Otherwise, looks like I wrote 1, 2, 3, 4, 5, 6 steps for 3 marks. How about a half mark for each step? Number 2, I took this right from the homework. Nobody asked me this question, and I thought that either means nobody did it, or maybe they all found it pretty easy. First thing that I did is I crossed out the 19 centimeters, and I said, nice try, 0.19 meters. And I crossed out the 88 RPM. Now, that is a frequency, but I said the frequency is going to be 88 divided by 60. To go from revolutions per minute to revolutions per second, you divide by 60. 88 divided by 60. And I said that's the frequency. This thing is rotating at 1.46 repeating hertz. And then I'm going to get the period. So I wrote this down, 1.46 repeating. And I said what I really want is the period, which is the reciprocal of this. 0.6818 repeating. So I said the period is 0.6818, and the 1/8 part repeats. I'm going to store that on my calculator. Now, what's the final speed of the spider? Well, speed equals 2 pi r over the period. It's going to be 2 pi .19. Couldn't even see that for a second there. I was blind. Over 0.6818, but I'm going to use my answer button, of course. 2 pi r over the period. And I said, okay, its speed is 1.75. Is that right? 2 marks for that, please. I would give you 1 mark for that, half mark for the number, half mark for the answer. Then B says, find the friction coefficient that's necessary to keep it in place. Yeah, I guess it would be its sticky feet that are holding it in place. And then when I saw that, I said, actually, it's the same free body diagram as the car. Replace the car with the spider, and this time the friction is being caused by whatever its stickiness is, but it's still going to be mu times the normal force because friction depends on how heavy the spider is. Now, the spider can clearly secrete some kind of a sticky substance. Well, that's just bumping up mu. That's why I put in brackets. I think here we'll find a mu bigger than 1, which actually for a bug made sense to me. I said, yeah! Because they can climb on the walls and ceilings. They probably do. So I said it's still going to be friction is what's pushing me in a circle. I got mu times the normal force equals m. I chose to use v squared over r because I noticed I had v still on my calculator. You could also use 4 pi squared r over t squared because you do know the period. It was 0.6818 repeating. So, and you could do it that way too. I don't know the normal force. Oh, but look. Mass cancels. And they wanted me to find mu. Hey, what's mu? I don't know. What's mu with you? And so I got mu equals v squared over g. Mu equals 1.75 squared over 9.8 times 0.19. This number squared divided by 9.8 times 0.19. You get 1.65 if I round off properly? Yeah, 1.65. Units? Nothing. And metric, can the coefficient of friction for a spider be bigger than 1? I'm pretty sure, yeah. Once again, I wrote down 1, 2, 3, 4, 5, 6 lines. I would go a half mark for each line. So what was that question? Caleb, was that from you or from Braden? You had a question? No? Okay. You were just being a nuisance? Absolutely, out of the 6 or so written questions that I was picking from, the Gravitron would be on it. Now, the Gravitron, the key is, can you get the free body diagram? Can you get the equation? And once you're there, I'll tell you, as far as I'm concerned, which things would be fair game to solve for. So in the Gravitron, this is a job for a free body diagram. What were the forces acting on the Gravitron? Get the obvious one. We had gravity down. Were you sliding down the wall? Were you sliding up the wall? So we knew there was an equal force here. At first we weren't quite sure what that was. Then we also knew what path we were tracing out. So there had to be a force inwards. And that was the wall. We said, you know what? That's the normal force. In fact, the Gravitron and space station artificial gravity are the same free body diagram. It's just that in the space station, since there is no Earth gravity, you don't need a vertical force canceling out Earth gravity. What is the vertical force canceling out Earth gravity? Okay. So we end up with this. Normal force is what's pushing me in a circle. Normally I would say, I don't know the normal force. Oh, but look. But I don't know the normal force, and I have no, oh, but look, but I have another equation that I can write. I can also write gravity equals friction. Gravity equals mu times the normal force. And the normal force is going to be MAC. So I'm going to get this equation here. mg equals mu MAC. Which version of A am I going to use? They gave me a period, so the one with the P in it. One with the T in it, sorry. I'm going to use this. mg equals mu M 4 pi squared r over t squared. Can grown-ups and little kids go on this? Oh, that's cool. Now, what would I consider fair game then? I would have no problem asking you to find either mu or r or t. I would just have to give you 2 of the 3. You know what? I'll bet you if there's 4 different versions of the test, and if I put this on there, probably on one of the tests I'm asking you to find mu, on one of the tests I'm asking you to find t, on one of the tests I'm asking you to find r, and on one of them I just did a random one, or I didn't put the Gravitron on it. What are they asking me to find here? Oh, r times by t squared divided by mu 4 pi squared, I think. R is going to be gt squared divided by mu 4 pi squared. 9.8. 3.2 squared divided by 0.45 4 pi squared. Why did I say minimum safe radius? If you play around with this, you'll find R can be bigger. Really, it's all about whether you're going to slide up or down. And so you can, if R is bigger, you can have a way smaller coefficient of friction, and you built in a big safety margin. You'd also be going faster, because the further out you move from the circle, the faster your your centripetal speed. The period wouldn't change. It's still 3.2 seconds. It's just as you go closer towards the center, you're going slower. As you move further out, you're going faster. So that was me being fussy as a nerd. 9.8 times 3.2 squared divided by bracket 0.45 times 4 times pi squared. You get 5.65 meters. If you got that, 7 out of 7. Otherwise, 1, 2, 3, 4, 5, 6, 7. Yeah, that'll work. Otherwise, I would give you 1 mark for that, 1 mark for that, 1 mark, 1 mark, 1 mark, 1 mark, 1 mark. Can you give yourself a lovely score out of 15, please? For those of you that were away last day, first of all, we finished off from lesson 4, the banked curve, and I'm going to tell you of those 6 or 7 written questions that are fair game for your test. As far as I'm concerned, having a banked curve is now, the banked corner is now fair game as well. It actually looked really tough, but you ended up getting a really clean free body diagram. The difference was there an angle? This was not a job for components. After all the habits I've built in on you, that I built into you, I said this time you're going to find, because we don't want the circle isn't parallel to the ramp, the circle is still horizontal, don't go with components. Instead, add the 2 vectors together. How would I add them together? Draw them tip to tail. Okay? So we looked at the banked corner, and then we started lesson 5 last day, where we looked at the roller coaster loop. This to me is also fair game as a written question, a roller coaster loop. And now let me pause. So roller coaster loops, they're a nice application. They're challenging because you're having to combine circular motion and conservation of energy. I do love the fact that when we calculated the minimum safe height, you get such a clean answer. It's 2.5 times the radius. We watched a video of someone doing the actual loop-the-loop. We noticed they got the same thing because we calculated the G-forces that you would experience at the bottom, and we said minimum, you're pulling 6 Gs. And we saw that the Cambridge prof, when he was calculating the number of Gs that the stuntman would be pulling, also got 6 Gs. Now, that's minimum. In real life, you don't build a roller coaster so that you barely make it over the loop. You build a massive safety margin, which means you have to be pulling more than 6 Gs at the bottom. This is why nobody builds circular roller coasters. I think I went on my little rant and I said roller coaster loops are what's called a clothoid loop. It's kind of a teardrop shape, and you can do a Google search or dig into that if you want to. The analysis of it for us is difficult because really, if you want the formal definition, Matt, it's a loop of continuously decreasing radius. And as soon as you have a changing radius that's always changing, you need calculus to analyze it. Calculus, once you get good at it, is designed to handle things that are changing all the time. We can't deal with that right now in Physics 12. But I will probably put because I'm nuts about roller coasters, you can certainly expect that the circular loop, the roller coaster loop, the badly designed but cool physics loop, that would be fair game. Another nice example is what's called the conical pendulum, example 2. You've probably seen these in malls if you've walked past a novelty store, especially right around Christmas. You'll see a toy plane attached to a string going around in a circle. And it forms what we call the conical pendulum. It's a pendulum because it's a mass on a string. Conical because it does form an upside down little cone. Did I just lose my image again? Boy. So, here's our question. It says this: a toy plane is attached to the ceiling using a string. The plane has a little propeller which causes it to move in a circle as seen below in the side view. Now, there are 2 forces we're going to ignore. It's coming towards us, and so the propeller would be coming out of the board towards us, but air resistance is exactly canceling out the propeller, so it's going around the circle at a constant speed. So we're going to ignore those 2. What's the best free body diagram for the airplane? Well, what are the forces acting on it? Get the obvious one. Gravity down. What else? Tension at an angle. Pardon me? That's it. Now, there is a force towards the center, but it's the vector sum of those 2. It doesn't show up on my free body diagram. If I add those 2 tip to tail, it is tracing out a horizontal circle. In fact, you may notice this is the same free body diagram as the banked corner, except on the banked corner, it was normal force and gravity. Here, it's tension and gravity. The correct free body diagram, then, is just that one there. But what that means is if we're analyzing this, Kevin, we're not going to go components. We're going to add these tip to tail like we did the banked corner. And otherwise, the physics is going to be pretty much identical. So it says, redraw a force diagram and then write force equations for the toy plane. So we said the forces acting on it are gravity and tension. We could do components, but here it's much easier to add these 2 together. How will I add them together? Draw them, Ange. And what I taught them last day on Friday was draw the easiest one first, the non-slanty one, gravity. The reason is, what path is this airplane tracing out, Ange? And it's a horizontal circle, so I know there must be a horizontal net force towards the center of the circle, which means I know to stop drawing my tension force right there. If I go further, or if I go shorter, if I go this long, I won't get a horizontal force towards the center. Or if I go this long, I won't get a horizontal force towards the center. That's why I draw gravity first. It gives me kind of my reference, and I know my second one has to stop there because I know what the vector sum has to be. There is FC. Where did theta end up? I notice that tension next to a vertical line is theta. Here's tension next to a vertical line. There's theta. ended up in the same place as our banked corners. Why I said it's going to be very, very similar. Let's do some trig, opposite, adjacent, hypotenuse. What's the tangent equation? Tan theta equals what over what? More specific in this triangle? What about cosine of theta? mg over t. And what about sine of theta? fc over t. Which one do I use? It depends on what they want, what they give me. Almost always, not always, but almost always, it'll be tangent, because usually you'll know the mass, you know, g, and usually you're wanting to find something about the moving in a circle. But you could also find tension this way. Okay, that's a little unique. I somehow moved one page sideways. I'll have to figure that out later. Okay, I'll have to figure that out later. Is that a blank page you have on the next page? And what does yours say? Okay, and mine is not showing this for some reasons. Let's click there. Let's click there. Let's click there. Let's come back to here. Ha, there we go. Example 3. A ball is swung in a horizontal circle, and it makes a single, quiet please, it makes a single rotation in 1.2 seconds. The cord makes an angle of 35 degrees with the vertical during the ball's motion as shown. Okay. What does A want me to find? Centripetal acceleration. You know what this is a job for? So it looks like I'm going to have, in this particular situation, gravity down and tension this way. And that's it. I realize there are angles. Am I going to go components here? No, I'm going to add these two together. How? Tip to tail. I'll get gravity down, tension up, and there is Fc. There's theta. Which trig function am I going to use to find the acceleration of the ball? The centripetal acceleration of the ball. That's your hint. I'm definitely going to be using Fc. Do I know tension? No? Then which one, Lena? Yeah, so I'm going to use opposite, adjacent. Which trig function? Tan. Tan theta equals Fc over mg. They're wanting me to find the centripetal acceleration of the ball. So I'm going to go mg tan theta equals MAC. MA, but we're moving in a circle. So, oh, see, I was really worried. I was thinking I was going to have to go either v squared over r or 4 pi squared r over t squared, and I was worried because both of those contain the letter r, the radius. Do I know the radius?
No.
Do I need to know the radius to find the acceleration? Okay. Not if I'm clever, because it looks like the centripetal acceleration is going to be 9.8 tangent of 35. And I'm good to go. 9.8 tangent of 35. And I get a centripetal acceleration of 6.862. 6.86. Is that right? Units, meters per second squared. What's B want me to find? Yeah, probably should say centripetal speed. If they did ask for a direction, I would say tangent to the radius. So I'll change that next year because I added this question this year, and I'll rephrase it. Speed, because we're not going to give a direction. Well, I could either find it, don't write this down, I could either find it by going v squared over r. Do I know A? 6.86. Do I know r? No. So let's file that away for a second. Or I could go 2 pi r over the period. Do I know the period? Yeah. Do I know r? Okay. No matter what, I'm going to have to find r. I'm going to use this method because that way I'm not using a possibly wrong answer to find another wrong answer, and it's not that much more typing. Anyhow. Okay. Apparently, I can figure out the radius. How? What else has the question given me that I haven't used yet? Braden. So if I hear you, you're telling me, how long is this cord? What does it say? 0.44? And what's the angle up at the top here? 35 degrees. Can't I use trig to find r? It's a similar triangle to my forces triangle, but this one is distances. And I didn't bother inverting it or adding things tip to tail. I just picked the triangle up from the side view. Which trig function is r in this triangle? Opposite? And which trig function is the 0.44? Hypotenuse. Which trig function am I going to use to find r? So I'm going to get this. Sine theta equals r over 0.44. How would I get the r by itself? Okay. So I'm not going to really write this down or memorize this. This is a derivation, and if it shows up again, I can find it in a couple lines. But apparently, if I know the length of the string, not the radius, but the length of the string, my speed is given by 2 pi 0.44 sine 35 all over, I've scrolled down, what was the period? 1.2. And that'll be my speed. Two pi 0.44 sine 35 divided by 1.2. I can get away without putting a times between the pi and the 0.44. Some of you might have to put a times sign on your calculator. Do you get 1.32? Meters per second. So that's the conical pendulum. Very similar to the banked curve. Really, the physics is nice. The key is, can you come up with the free body diagram, add them tip to tail, and get the trig portion. And once you're there, it's actually much cleaner than a lot of the stuff we've been doing. An object moves in a horizontal circle on the end of a string as shown. If the tension is 42 newtons, A, what's the net force on the object? And B, what's the period of revolution? You know what this is a job for? I think so. You know what? I'm going to be really lazy. I'm just going to label my forces. So I know I have gravity down. I have tension. I'm going to add those two together, tip to tail. I'll get mg tension. I know to stop tension there because this object is traveling in a horizontal circle, and so the net force has to be horizontally towards the center. And the 18 degrees ends up at the bottom because when tension is next to a vertical line, it forms an 80-degree angle. So there's tension next to a vertical line. There's tension next to a vertical line. Spencer, what does A want me to find? What's the net force in this picture the same as? Fc. So, although it says find the net force, I'm going to find Fc. Opposite, adjacent, hypotenuse. Which trig function? What did they tell me in this question? Tension or mg? Tension? Then I'm going to use those two. Which trig function this time? Yeah, sine. I see the sine. Sine of theta equals opposite over tension. And since they just said find the net force, I'm not going to plug in MAC or MV squared over R or M4 pi squared R over T squared. I'm just going to get the FC by itself. The net force is going to be the tension times the sine of 18. It's going to be 42 times the sine of 18. And I get 12.97. You know what? 13.0 if I go to 3 sig figs, I think, yeah? There's the net unbalanced force. That's what's causing it to accelerate towards the center. B. Oh, you know what? They did give me the mass. I could also have used, I guess, mg, and I should get the same answer. I hope. Unless I was making up numbers and didn't make sure that they all worked, but they should. B, what's the period of revolution? Okay. Let's start out with the same starting point. Let's use tension again, but instead of Fc, let's write M4 pi squared R over T squared equals T sine. Uh-oh, what's the problem here? What's this T down at the bottom here? Period measured in seconds. What's this T here? It's a force measured in. So I'm going to scribble that out and call it Ft, so I don't get mixed up. That also reminds me, somebody pointed out today, was it, no, I think Rick or Mitra, there's a mistake on my formula sheet, good gosh. I suddenly realized that on the back page, when we're looking at the different planets, and when the formula sheet doesn't show up, it kind of is frustrating. Let's bring this back. I have the period of the orbit around the sun, that should be seconds, and the period of the orbit around the Earth, that should be seconds. I think those are the only two that I have the wrong units on. I must have been cutting and pasting foolishly, because period is measured in seconds. So you can fix that on both your blue and your yellow sheet. Sorry. Don't know what happened. Getting old. What am I trying to find in B? Okay. How would I get the period by itself? I think times it to the top, divide the tension and the sine over, and square root. It's going to be M4 pi squared R all over tension sine 18, square root of that. What was M? I've scrolled. Oh, 3.5. It's still on my screen there. 4 pi squared. R is 0.6. Tension is 42 sine 18. 3.5 times 4 pi squared times 0.6 divided by bracket 42 sine 18. Close off the bottom. You get a period of 6.39 seconds. Kevin nods. Anybody else? I don't trust Kev. Anybody else? Am I wrong? Oh, square root. Good gosh, Kev. You and I both. How about 2.53? I haven't done that one for a while. I am the king of mistakes, by the way. I was always good for losing one dumb mark on every test. That's why I tease so many of you that do that, because it's me. Put your pencils down, look up. What's your homework? You can try number 1. Try number 2. Now, what's the diameter of the loop in question number 2? What's the radius? If you go 2.5 times the radius, if you recall what we calculated, that's 24. This is 25 meters. You're not going to have a normal force at the very top of the roller coaster of 0. There is going to be a little bit of normal force. So number 2 is a little tougher than I've done with you. See if you can figure it out. Okay. Number 3. 4, 5. 6. I'm going to skip 7. Then suddenly all the questions have vanished. Is that it? Oh, no, there they are. Yay. 10 is good. 9 is good. I don't know. Yeah, apparently 10, 9, 10. I need to fix that. And then I'm missing a page again, Mr. Dewick. $11 is good. 12 is good. What is going on here with me missing questions? 13 is good. 14 is good. So you got 20 minutes. Next class, I'm just going to be giving you a take-home quiz. We'll mark the take-home quiz on Monday. The take-home quiz is going to have some teeth to it. It's going to have on it roller coaster loops, banked corners, conical pendulums, all this stuff.